An open pasture is to be enclosed with wooden fencing to make 5 adjacent corrals. Each corral will be shaped like a rectangle, with adjacent corrals sharing a whole side in common, so that the corrals are lined up. So we're not talking about, there's 4 corrals and there's another one. No, they're saying they've got to be lined up. So we really can only draw the one picture. 1, 2, 3, 4, 5 corrals. This is the idea. This is the picture we're working with. All right. If each corral needs to enclose 1,500 meters squared, what is the minimum amount of wooden fencing that is needed to enclose them? Okay, so a minimum here, we're looking at an optimization problem. But we do have a constraint. We can't just make really, really tiny corrals. They do have to enclose a certain given area. All right, so what have we got? What are we working with? Well, we've got these 5 lined up corrals. Now, we're talking about the area of them. We know the area of each one has to be 1,500 meters squared. So how do you find the area of a rectangular corral? Well, you need to know its length and its width. But since they're rectangles, we're going to have the same length each time, and so we'll have to have the same width each time. So we've introduced some variables, x's and y's, to help us sort of figure out what's going on. And we can see the area of each corral is x times y. X times y must be 1,500. Okay, we can actually rearrange this into a constraint function. Okay. Now, what are we trying to do? We are trying to minimize the amount of wooden fencing. Using our x's and y's, can we express how much fencing is being used? Well, yeah, we've got 1, 2, 3, 4, 5, 6 x's. And then 5 on the bottom, 5 on the top, 10 y's. That is the amount of fencing that we have to work with, or that we will be working with to make our corrals. So it is this that we want to minimize, subject to this constraint. So that's constrained optimization, and we get ready with a Lagrangian. Okay, there we go. Now, how do we do a constrained optimization problem? Once we've got our Lagrangian, using our Lagrange multiplier lambda, we find critical points. So derive with respect to x, derive with respect to y, and then derive with respect to lambda. And to find critical points, all of these have to be 0. All right, so what can we do? Well, the first 2 can very quickly be rearranged to say minus 6 is lambda y, or I guess you could say minus 6 over lambda is y. And a good strategy, especially if you get stuck doing constrained optimization, is to try and get everything in terms of your Lagrange multiplier lambda. Failing that, try and get everything in terms of an x or a y, but usually getting everything in terms of lambda is quite good, because then you can just plug it into the constraint function at the end. That's a very good strategy I've found. So we've managed to do that. We know y in terms of lambda, we know x in terms of lambda. So let's plug them in. Minus 10 over lambda, minus 6 over lambda, minus 100. Well, we can just bring it over to the other side and say equals 1,500. So that's 60 over lambda squared is equal to 1,500. All right. So where can we go from here? We need to solve for lambda. Now, it's a quadratic, so there might be a couple possible values for lambda. One thing we could do is rearrange it and say lambda squared is 60 over 1,500. We can drop a 0 from both sides, just divide top and bottom by 10. Divide top and bottom by 2, we'll get 3 over 75. Divide top and bottom by 3, we will get 1 over 25. So now it looks like lambda is plus or minus 1/25. So each choice of lambda will then give us different values for x and y, which will give us the dimensions for the corrals. And then we can work out the amount of fencing used. Okay. So, well, where do we go from here? Well, if we let lambda be 1/25, and we can get x and y, so we'll get minus 6 over 1/25. And that's really just minus 6 times 25. And 6 times 25, so it's going to be minus 150. Minus 10 over 1/25 is going to result in minus 10 times 25. So minus 250. Okay. So there we go. We've got our x and our y's. Oh, wait, hold on a second. I forgot to square root. These numbers felt way too big. In my head, the way I checked this, I was mentally double checking because x times y should give us the area of the corral, but 150, a little too big. A little too big. So it's actually 5 we need here. There you go. So always be thinking through it. Don't just blindly be doing your calculations. So we get minus 30 and minus 50, and that makes a lot more sense. Okay. Except for the fact that these are sort of impossible lengths. But yes, technically minus 50, minus 30 is a critical point. It's just not a terribly useful one for us. Okay. We might just discard them and say, hey, impossible lengths. You can't have minus 50. And that's something to take into account. When you're given a word problem, as opposed to just a bunch of formulas, you have to make sure that the answer you get makes sense in terms of the word problem. You can't have things like negative volumes and negative lengths. Okay. So that really only leaves us with one other option. Okay, negative 1/5 for our lambda. Certainly possible. Okay, and so our x will be, oh, x is the negative 10 one, because x was the longer side. Negative 10 over 1/5, and, negative 1/5, and that will be 50, which makes a lot more sense. And negative 6 over negative 1/5, the minus signs cancel out, and we get 30. So our corral should be 50 by 30 in their dimensions, but that is not what we were asked for. Okay. We want to know what's the minimum amount of fencing. So what's our fencing formula? 6x plus 10y. So 6 times 50 plus 10 times 30. And that's 300 plus 300. So 600 meters of fencing is needed. Okay. And there we go. Now, if you had gone ahead and plugged these in, you would have said, oh, I need negative 600 meters of fencing, which admittedly is a smaller value. And that's why it's really important to stop and think about the numbers you're working with and the answer that you are giving.